And here we are, chapter 9, the last chapter. This will cover safety, variety of topics that were mentioned in the chapter. And I thought what I would do is kind of start off with the basics of electrical house wiring. Um, just wanted to kind of explain how the electrical system for power in your home is set up. And that may, if you're not familiar with it, um, it may give you a little understanding. And even if you don't do the electrical work yourself, if you understand it a little better, I think if you happen to work with an electrician on a project, it might make it a little easier. So the way the power gets into your home, obviously you see the power lines on the power poles running through your neighborhood, although sometimes they could be underground as well. But it's usually transmitted. The power is distributed at a fairly high voltage, and in order to make that voltage usable in the home, you have to go through a transformer, which takes I don't know, let's say 12, 13,000 volts at the power pole and transforms it and drops it down to 240 volts on the house's side of the transformer. So this is the transformers usually sitting out there up on the pole. Could be a gray metal can with wires going in and out. And then a power feed's brought into your house, and it's essentially three wires. There are two hot legs and one neutral. And the neutral is established by the center tap of the transformer on the secondary, and they'll connect that to ground. And then what you end up with is AC voltage. And if you measure with a voltmeter from ground to this leg, you have 120 volts. And if you measure it from ground to this leg, you have 120 volts. And if you measure across the red and the black wire coming in, you'll measure 240 volts. So this is how two different operating voltages are delivered to your house. You can pick up 120 volts here, you can pick up 120 volts here, or if you have a higher voltage, higher powered item like an electric stove or an electric dryer, your air conditioner, then they're connected across the 240 volt inputs. And then in terms of the way the things are actually connected, um, each of your devices, you want to be able to do a couple things with them. One is you want to be able to turn on and remove the power, and that's what a circuit breaker, one of the functions of a circuit breaker. And the other thing you want the circuit breaker to do is to protect the power feed to the device, whether it's a light bulb or refrigerator or whatever, so that if there is a problem with the device and it starts drawing too much current, the circuit breaker will automatically open up. And so those are the two functions of the circuit breaker. And on the 120 volt side, you'll have one breaker for each item that you've got wired into your house, or items. Sometimes you'll string several outlets on one breaker. And then to get 240 volt devices over here, you'll have two circuit breakers. They're side by side physically in the box, and we'll take a look at that. But they are mechanically connected so that if one trips or one is open manually, then they both open up and disconnect the 240 volt device from the uh, incoming line. Now, this is a picture of a typical residential power system. Uh, in this case, the main power is coming in from the bottom and comes up here to the top. And here's one leg of the main power. And here's the other leg coming in and feeding here. And so what you have from here to here is 240 volts. And then there's a bar that runs through the panel all the way down on this side that carries um, this side's voltage, and then a similar bar on the other side, and then neutrals in the center. No, I don't think that's a neutral. Forget that. So you've got this side energized with this power lead, this side energized with this power lead, and as you come down, you'll see all these circuit breakers, and then the wires that are going through your house are wired into the circuit breaker. So your circuit comes in here, goes out the breaker to the item in the house, whatever's being wired, and then the neutral wire is brought back here to these neutral terminals, and the ground is also brought back to there. So you got 120 volts on this side, 120 volts on this side, and then there will be breakers. Take a look at the next picture. So this is the main breaker up here. This one's rated 200 amps, and when this breaker is thrown, the power to the house is disconnected, and it's also a safety over current trip, that if the panel starts drawing more than the rated current, it'll open up and shut everything off. So you can see the neutrals here. Couldn't see it as well in the other picture. The neutrals are here, the white wires. So it's 120 volts from here to here, and 120 from here to here, just like we saw on the schematic. And then down here at the bottom, you can see this breaker, and I think the next slide's a zoom in on it. Let's go ahead and go to the next slide. But you can see that this breaker is actually two breakers mounted side by side. So one is fed from this side, and the other one is fed from this side. So you get 240 volts across here, and they're mechanically ganged together. You can see that's one bar. So that if one breaker or the other trips, either manually or due to overcurrent, they both will open up. And then these are just some graphical representations of different types of 120 volt plugs. You have a neutral and a hot and a ground. This is kind of typical of what you have for computers and other electronic components. And this is the view from the back of the receptacle. So when you're looking at a receptacle, if it's wired properly, you'll notice that one opening is smaller than the other. Well, the larger opening here, or on the right, if you're viewing it from the back of the receptacle, this is the neutral. And then the other one is the hot wire coming in. And then the ground goes back to the ground rod that's probably outside of your house, as close as they could get it to your electrical panel. And taking a look at current carrying capacity of different size wire. Wire is, at least in the U.S., it's specified by AWG, or American Wire Gauge sizes. And in a gauging system like this, the smaller the number, the larger the wire. So what we end up with is, say at 14 gauge, 14 AWG, has an allowable current of 20 amps, but the breaker, according to the National Electrical Code, needs to be set at 15 amps. So that way the breaker will trip before you get into an unsafe area with the wire. 12 gauge can carry 25 amps, but it's fused at 20. This is what a lot of your house wiring, 14 and 12, are what's used for most of your 110 volt house wiring, the outlets, ceiling lights, those kinds of things. And then you start getting into the heavier wire, the 10 gauge. Allowable current's 30 amps, and it can be fused at 30. 8 gauge is 40 amps, and 6 gauge is 50. Now, where this may come in at a later time is if you want to buy an amplifier, an HF amplifier, say a 1500 watt amplifier, unless you happen to have a service already in the house, you'll probably have to add another run of either a 40 amp or a 50 amp breaker if you want to operate the amplifier safely. And the supply current and voltage will be specified by the amplifier maker. So you'll just want to make sure that you, if you know, you're getting the installation of the proper size wire and breaker for the load that you're going to have on the amplifier. This is a look at how you should ground your equipment in your shack. And the idea they're presenting here is that they take a copper pipe or some sort of bonding bus and have every item in your shack grounded to that bar, and then that bar is grounded outside through a strap to a ground rod. And the thing you want to avoid is a grounding system where you ground, say, from this device to this device and then to the ground, because you can get ground loops set up that can cause problems. So basically, the way I describe it is kind of a star pattern or a radiating pattern for your devices. Now, let's go to the next slide. Now, if you remember this is my initial setup of my home shack. So this picture is right out of the your book, and what it's showing are different devices you can use to help protect the power system and do some things to suppress noise that you may have in your systems. An example here, they're showing on a television on the antenna. They have high-pass filters that you can install in line with the television antenna, and what that does is if you have noise below the television frequency, this high-pass filter will only let the television signals through and attenuate or reduce the lower frequency signals. They're also showing a ferrite cord on the AC line cord, and what this does is it helps suppress current surges. And what happens there is that, say you do have a power surge and you start flowing current at a higher rate to the TV, the ferrite core will absorb some of that energy, because what it's doing is it's absorbing the increased magnetic field and helping to dissipate some of that rather than getting all of that into your TV system. And you can see a similar thing can be done here on a phone system where you use the ferrite core. It helps attenuate the current noise, and then the low pass filter on the signal will just let the audio through and attempt to filter out higher frequency noise components. And we're showing a transceiver here. You can put a low pass transmitting filter to the antenna to take some of the noise out. Now, my experience has been I haven't had to use any of these filters. I do use ferrite cores, but that's primarily for surge current protection. Use the ferrite cores in conjunction with a surge suppressor for either the device or for the house. You can get whole house surge suppressors, and they work together to keep high voltage transients out of the house. That's what the surge suppressor does. And then the ferrite core helps to attenuate the current surges that you may have during a power surge on the main power lines. I think the reason I've been fortunate that way is a lot of it has to do with the good grounding. If you have good grounding systems, that's a good way to knock out and prevent a lot of noise from getting into your system. But every setup's different, so you may have different situations and may have to work through different solutions. These are just showing some different types of ferrites that can be used. These are iron, special alloy iron type cores. They're like half cylinders, and what you do is you put the power line in here and it'll close and snap shut going around the power line. Okay, there's we're switching gears here a little bit. Now we're looking at exposure to radiated energy. And this is right out of the book also. And it's got all the details on the power thresholds for RF exposure limits. Now, there's two levels of exposure that need to be evaluated in your home, in your shack. And one is considered a controlled area. That's the area that you have control over. And then the uncontrolled area would be an area that you don't have control over, like your neighbor's property or your neighbor's house, that kind of thing. And you can see that the permissible exposure levels are, the standards are lower for an uncontrolled environment than they are for your controlled environment, because they would expect you to know what you're doing, and you know that the equipment does radiate energy, and you should know enough, you'll be trained enough to deal with it. Okay, I just had a pop up on the screen. I hope it doesn't show up on the video. But the other thing to note is that the power density threshold changes with frequency. Where you can see here in the 30 to 300 megahertz range is the lowest threshold for power, and VHF just happens to sit right in there. UHF is oops, got to get my lightsaber back so everybody can see. Okay, so this is the frequency, and this is the exposure limits for both controlled and uncontrolled environments. And you can see that as the frequency increases, the exposure limit goes down, meaning you can't have, it reduces how much you can be exposed to. And the worst case is in this 30 to 300 megahertz range. So the VHF 2-meter band is right here at 140 some megahertz. And then 440 is right outside of this 300. So these are the areas that have the lowest threshold limits. It's also the area that typically the radio operates at a lower power than you have in the HF. The basic transceiver that you would use for HF transmission will typically be at 100 amps, or excuse me, 100 watts, and a base or mobile unit on VHF or UHF will be at usually no more than 50 watts. So that all enters into it, to how all this is established. So this is the jargon, the wording that went along with that graph we looked at, which is down here, and I noted the VHF, UHF section, and then the HF section up here. The thing that people need to understand the difference between the radiation we're dealing with here, the electromagnetic radiation, and the atomic type radiation, is that the electromagnetic radiation is non-ionizing, and it's much weaker than the ionizing radiation that you would get from nuclear materials. Let's see, you probably read all this, but I just kind of highlighted these things out here, and I'm going to show you an example. Things are really kind of distilled down to a pretty easy way to evaluate your station when you get it going. Okay, so what we're going to do now is take a look at how you go about doing these calculations, and they've really got it set up so it's easy to do. What I've got here is an analysis I did for our Hextena antenna, and the Hextena is just a simple dipole antenna that we use for Parks on the Air, where we go out and activate parks, and Judy makes contacts with people all over the country. And what I wanted to be able to do is that if somebody ever walked up to us and started asking questions and asked me about the safety of the antenna, I wanted to be able to show them a document that I'd prepared that shows how safe the antenna system is, and the federally defined distances you need to stay away. So if you go to this website, arrl.org, they have a calculator, which is this down here. It's a screenshot of the calculator. Let me get my pointer back on again. Okay, so here's the ARRL website you would go to, and this is the exposure calculator. And the first thing you have to put in is the power at the antenna. Now, I've overstated the power because my transceiver can output 100 watts, but there's going to be loss in the feed line, and there's going to be loss in the reflected power coming back from the antenna because we're not operating at an SWR of 1. So there's going to be considerably less than 100 watts being radiated. But just to be safe and on the margin of error to the good, I said, okay, let's say we got 100 watts radiating from the antenna, and then you specify the mode and the duty cycle, and we typically are running single sideband or phone. And if you were running digital, there's a drop down selection for digital modes or CW. And then you describe your transmit and receive pattern. I said, okay, we're transmitting about the same as we're receiving. And then the antenna gain, they say dBi. Now, if you recall, dBi is the measurement of the antenna gain of an isotropic antenna. That's that imaginary antenna that can't be built, where it's just a point in space. So that means, this being a dipole, the antenna gain for a dipole is 2.15, above that of a isotropic. And then the operating frequency that we want to operate at. And what I did is I took the middle of 6, this would be the middle of 6 meters, and then I did the middle of 10 meters, 12 meters, 15 on up to 40. So I would cover the whole band that this antenna can operate from 6 to 40 meters. And then I went through this and just kept changing the frequency. And I just put this in a table so I could print it out and draw a graph. But what this is showing you is that the RF exposure limits at the ranges that we're looking where we normally operate, the 20 meter and 40 meter here on the graph, that the see which one is it here? Minimum safe distance, which would be the solid lines. You can see the minimum safe distance for the controlled environment and the uncontrolled would be about a foot. You need to stay about a foot away in an uncontrolled situation, and you won't ever exceed the maximum allowable absorption. So, it's pretty easy to keep people a foot away from something like that, particularly if you're standing there about 20 feet away from it talking to them, and they can see, and it should make them feel pretty comfortable that, it is safe. You'd have to, probably the biggest danger is if you touched it while you're transmitting. Sometimes you can get an RF burn, you burn your finger. But it's really, at this power and this type of antenna, it's a very safe operating environment. And so I just did that for each of the bands we're at. And you could see if we start going, say if we go to 10 meters, then we'd probably want to keep people 5 to 10 feet away, which we want to anyway. We don't want them that close. And we've got yellow tape if it's a particularly crowded area, we can set up to keep people away. So that's how I dealt with concerns about radiation exposure. And I've yet to have anybody ask that question, but if they ever do, I'm ready. And finally, this graphic came out of the book, and it just shows you what I call the knobs you can turn to make adjustments to the exposure that a particular setup has. Obviously, one thing you can do is you can reduce the antenna gain, and that can be done by changing the dimensions or the type of antenna. You can point the antenna away from, say, if you're concerned about a particular area, neighbor's property or whatever, you could point the antenna away if it's a directional antenna. You can keep people away. You can move the antenna away from people, and you can reduce the average power. So any of those combination of things, if you would happen to run into a situation, and that would probably be most likely if you were dealing with a 1500 watt amplifier and a very directional antenna, a multi-element Yagi. These are the things you could do to make adjustments in your exposure calculations. So that'll wrap up the last chapter. I hope these videos have been helpful. At the very least, I hope they didn't confuse anybody. And if you ever have if you're at this point in your studies, and let's say you're not from our area or don't keep in touch with us and need to find a testing site, just let me know. You can reach me at k3sks@yahoo.com and help you find the site or answer any questions you may have. And if you have any suggestions to make this better, I'd appreciate those too. So this is my sign off. I'll say 73 to everyone. Good luck on your test adventures. But I think if you're working at it and doing the reading, doing the sample questions, doing the practice test, watch these videos, you're going to be more than prepared enough to pass the test. So I expect good things that you guys will have on as you progress through the ham licenses. So I want to say 73. This is K3SKS, and I'm QRT.